Hello, I'm Sumi, and I will be going over homework 2 for BME 204. Before we get started, there's just some important resources for this particular chapter. So body-centered cubic, obviously to find the edge length A, you would take 4 times the radius of the ions or the atoms you're using, divided by the square root of 3. For a face-centered cubic, FCC, the same formula except it's divided by square root of 2. And for HCP, it is A equals 2R. Like I said, A is edge length and R is the radii. Atomic or ionic depends on what we're calculating. Here's just a list of typical metals with each structure. Just might help if we're looking for something very specific. Moving on, for unit cells, except for hexagon, which is the HCP, the faces contribute to 1/2 of an atom, the edges contribute to 1/4 of an atom, and the corners contribute to 1/8 of an atom. So this will be useful when we're calculating how many atoms are present in a unit cell or how many atoms are present in a particular direction. So I'm just going to keep going. So question 1 and 2 ask us to find the ionic packing factor. Obviously, we all have answer keys, and we're not here to just look over the answers. So I did come up with how we would conceptually get to the answer. So 1, using the relationship between unit cell size and atomic radius, you find A, which is the edge length of the unit cell. And then you find the volume of the unit cell using A cubed. Then moving on from that, you have to find the volume of the ions by first finding the number of ions in the unit cell, which I will talk about more when we're actually doing the question. After you find the number of ions in that unit cell, you would multiply that number into the volume of a sphere, which essentially is the volume of the atom itself. Atom or ion in this case. So the formula representation of that would be the number of ions into 4 divided by 3 pi r cubed, which is just r would be our ionic radius. And then IPF, which is the ionic packing factor, is volume of the ions divided by volume of the unit cell. Now the first question talks about UO2, which is based off of CaF2's crystalline structure. Now it is an FCC, but we use the BCC equation for finding the edge length because of the fact that, if you can see on the right here where my cursor is, there is absolutely no oxygen atoms if we do use the face diagonal, which is 4r divided by square root of 2, which is the FCC for finding, the formula for finding A for an FCC. But in this case, we do have to use the body diagonal so that we include the oxygen atoms in our calculation, because it is technically inside the unit cell. This threw me off a couple of times, and I'm pretty sure it threw everybody off because we did have quite a long debate on whether to use the FCC formula or the BCC formula. And I think most of us went with what was in the textbook, which was the BCC formula, which is square root of 3 divided by 4. A equals the radius. Now, doing that, you find A, and that's 0.48 nanometers. And going on from that, you find A cubed, which is the volume of a unit cell. Now the number of ions, yes, it was given in the problem for CaF2, and we just went based off of that. But if we were trying to actually find it given just the drawing and not the actual number of ions in that unit cell, 1 into 8 would give us the corner atoms of U4+, plus half into 6 faces that we have on a cube would give us the face atoms. So that would give us a total of 4 ions of U4+. So like I said before, each corner position is 1/8 of an atom, or 1/8 of an ion in this case. And then you would add it up and you would have the number of ions that exist in that unit cell. Now, oxygen's all inside the unit cell. I don't know if you can tell from my drawing because it is horrible, but it's right here. I'm just going to go draw it so that everybody can see it. It's right there. So you got 1, 2, 3, 4, 5, 6, 7, 8. I counted faster than I could draw. All right, there we go. So we have 8 oxygen atoms all inside the unit cell. So when we're doing our calculations, we need to keep in mind that we have 4 ions of U4+ and 8 ions of O2-. So that comes right back down to here. We use the radius, the ionic radius. Please be careful because I made that mistake twice and I used the atomic radii instead of the ionic radii. They're right next to each other on the appendix. It is really easy to mix it up. Going from that, we calculate the IPF, which is the volume of the ions divided by the volume of the unit cell, and you get a dimensionless number right here. This is just a tricky question only because we're using BCC instead of FCC when the actual structure for UO2 and CAF2 is an FCC. Please keep that in mind. Here's a better looking structure of how the CAF2 looks. So you can see that all the calcium, not the calcium, well, yes, is inside the outer cube. Now moving on, we have the zinc blend, which has the structure shown over here. This is my rendition of it. Obviously it looks nothing like that, but it's fine. You walk through the same similar steps. You find the number of ions. In this case, you have 4 ions of S2- and 4 ions of zinc that are all inside the unit cell. So in this case, there's a better representation on the right where you have 4 blue zinc ions that are all inside the unit cell. Use the same logic, find the volume of the ions, and then find the IPF. Moving on to question 3. In this case, we're trying to find a series of directions that are in the 110 family that lie on the 111 plane. So the idea behind it is that if we find the dot product of the normal vector and, not a normal vector, I said vector, haha, the direction normal to the plane and another direction, it should equal to 0 because it is perpendicular, which means it does lie on that 111 plane from this particular family. So you do that and you get these 6 set of vectors. I need to stop saying vectors. I'm so used to saying vector notation, so this looks a lot like that. It is an easier way to picture it if you are thinking about it, is thinking of it as a vector. Anyways, you take the dot product of these 2 directions and you should be able to get 0, and that gives you perpendicular direction. There's really no better way to explain this. I really wish I did have a better explanation for this one. Quick thing to keep in mind is the notation. Square brackets are for direction and the normal parentheses are for planes, and a 1 with a bar on top of it is a -1. I did mess that up on my own homework, so this is all redone. And yeah, this is using that formula that's given on that page and the idea that if a direction is perpendicular to a plane, that the dot product of another direction will give you a perpendicular dot product of another direction will give you a family of directions that lie on that plane. Now, question 4. First 3 lattice points in the 112 direction in the FCC lattice. So 0, 0, 0 is the origin. 1 half, 1 half, 1 is technically the middle of a first unit cell. And 1, 1, 2 is the corner of the second unit cell. So if you can see here, it's depicted like that. Remember, unit cells are all 1 by 1 by 1, so you can't have a unit cell that's bigger than that. So you would have to add another cube to get that extra 2 in what I would like to call the z direction at this point. Moving on, we have about 8 sets of Miller indices here. This is fairly simple if you don't forget to take the inverse of the plane indices that they give you. I ended up doing 16 cubes because I did not do the inverse in the beginning, the first time around that I did it. So the idea to draw these planes is that, first of all, you got to state clearly where your origin is, or where your center point that you're basing everything else off of is. The second thing is take the inverse of the coordinates provided. So for this one, it's 1, 1, 1. You would take the inverse of 1, 1, 1, which is still 1, 1, 1. For example, here, this is 2, 0, 0. If you take the inverse of 2, 0, 0, you get 1 divided by 2, and 1 divided by 0, and 1 divided by 0. So this leads to infinity. Infinity is just all points on that plane. So for example, here you have all points on the on the z plane and the y plane. So going both directions, you have all the points. You do, however, move half in this direction. So we can consider this as the A1 direction or the X direction. I just prefer to call it things that we've already seen before. So the XYZ coordinate plane is not something that is unfamiliar to us. Moving on, similarly, you have 1 half, 1 half infinity. So we're still going infinity in the z direction, which just means all the points in the z direction. I would draw that better, but I could not. So here you would just take 1 divided by 2, 1 divided by 2, you have half movement in this direction and half in that direction. Number 4 is 3, 1, 1. So this is just 1/3 in the, what I would say again, as the A1 or X direction, and then you got this one, you got that, and you move 1 in this direction and 1 in that direction, and then you would connect these points to draw the plane. Very similar approach to number 5. This is also a very similar approach where you have 2 infinities again, except instead of moving half, we move 1/4 in this direction. This is 1/3 in the X and the Y, and 1 in the Z. And you have a very similar approach here too. This is again infinity. The most crucial thing is do not forget to take the inverse of it. Do not make the same mistake I did. Drawing cubes are not fun. Question 6 is drawing the plane and then sketching the direction in that plane that goes through those atoms. So this is actually a BCC plane, which I forgot to mention. I'm just going to write that here in the worst way possible. So we do have a atom in the center. So the important part about this again is sketch your plane first. So the 1, 1, 0 plane is, again, you take the inverse. You got 1 in the X, 1 in the Y, but you got infinite points in the Z direction, or the A1, 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 A2, A3 directions. So now the crucial part is trying to figure out which direction to draw the arrow in. You can go from here to here, or here to here. Now we need to go -1 in the y direction, in what I would consider the y direction. So we're going backwards this way, which means the arrow needs to go like that. We are still going in the positive x and positive z, or what we can call positive a1 and positive a3. I do know that we should probably use proper notation, but this is what we got right now. Actually, I don't know why cristobalite is here, but why did I put that there? Oh, okay, we'll come back to that. So the next question is about linear density. Linear density is number of atoms in the direction that they give you divided by L. And L is the relationship of the given direction, and A, which is the edge length. So for this problem, we're going in the 1, 1, 1 direction, which is from here to here, as you can see. So you do some simple trig and you figure out what this is. This is square root of 2a, and this is a. You do more trig, and you get square root of 3a. L is equal to square root of 3a. And now you use the relationship between a and r from a body, a BCC cube. Again, I think this one is the one where we use UO2. And I remember us telling, the FC, though UO2 and CaF2 are both FCC, we do use the BCC formula because we have to include the oxygen atoms that are in the center of the cube. So you use that, you rearrange your terms to get L, which is square root of 3. And square root of 3, using that formula, is 4r. And then you solve for you solve for L. And then here's the important part. So when you draw out the FCC structure for UO2, you get one. When you draw out the FCC structure and then you draw the direction 1, 1, 1, you get 1 ion of U4 plus and 2 ions of O2 minus. Using that, you do the same formula that I gave up here, which is linear density is equal to the number of atoms divided by L. So we have number of atoms, or ions, divided by L. And that gives us this value right here. Question 8 follows the similar process in where we do the same thing as we did in number 7, and we get the same answer, well, similar answers. And then question 9, which really, really threw me for a loop because I did not even understand what they were asking for. But the easiest way to explain this is thinking of these, well, I don't want to say the wrong thing, but thinking of these atoms acting in pairs. So we have the first 4 points given to us. So these are all either, well, these are face atoms, and this is a corner atom at the origin. And we're trying to find that pair atom that is a tetrahedral connection in this cube. So you have, I'm circling the 4 black ones that are connected to other atoms. So the idea behind it is just finding these pairs. So we got right here. And finding the directions for them. So let's talk about the first. I'm going to undo all that so that we can clearly write it. So 1/2, 1/2, 0 is the one that is on, let's see which plane that would be. 1/2 in the x direction and 1/2 in the y direction, which is right here. So that is, I love how I'm pointing at the screen like you guys can see it, but so 1/2 is right here. So that's the first one. And we're going to find the closest atom here that is bonded to 4 other atoms. And that would be 3, and we're still considering this as our origin, so let's not forget that's 0, 0, 0. And that would be 3/4 in the x direction, 3/4 in the y, and 1/4 in the z. We know that well, how do I say that? I'm going to pull up the textbook real quick so that I do not say that in the wrong way. So we do know they're 1/4 away from each other in diagonal length. That was mentioned in the problem when it was given to us, which is why we're getting these 3/4, and they're also connected to 4 other atoms, which is a good hint. Anyways, back to what I was saying. So that's the first pair. The second pair is 0, 0, 0, so that's right here. And that would just be 1/4, 1/4, 1/4 in all 3 directions. Number 2 is 1/2 in the x and 1/2 in the z, which is this face atom right here. And we find the closest pair, which is another atom that's bonded to 4 others. And we find, again, the directions for those. And that would be 3/4 in the x, which is 3/4 this way. Would be 1/4 in the y, which is this way. And then we have 3/4 in the z. I need to stop using that notation, but it's easier to understand. Similarly, you have number 3, which is 0, 1/2, 1/2, which is, I believe, if I'm right, this one. And then the closest bonded to that is right here. So you find these pairs, and that's what gives us the points right here. This is the easiest way to explain this because of the way that this diagram is set up. If I were trying to explain it with the diagram in the textbook, I would find it near to impossible. But yep, that is my best explanation of this. I know Carl, for a fact, has a better explanation than me. So if you have any questions, please ask him. And then question 10. Question 10 uses 3 different formulas, which you need to keep in mind. One is this A to find the edge length. You use this formula, which is the FCC formula. Then number 2 is this one, which is the X-ray diffraction formula to get theta, the angle of diffraction. And D, to get the D that's over here, you use A divided by, well, this should be A1 plus A2 because we're following proper notation. I wish I could write better. And then you square all of those, and you square root them, and you get D. And then you plug in D into this equation. So this we're given in the question itself. It's provided. We're moving on. You solve for D11, which is A that we get from solving over here. Plug it in. You get square root of 3, which is just, for D11, it would be 1 plus 1 plus 1, because 1 squared plus 1 squared plus 1 squared divided, and then square root it. You get this number. You take this number and you plug it in over here. You actually need to rearrange this equation to get that before you start plugging anything in. You solve for theta, and you get theta. But do not forget, when you need to plot, you need to multiply into 2 so that it's 2 theta and not just theta. I had to redraw my graph, so let's not make that mistake. You go through the entire formula 4 times for the different directions, and then you plot. Now, keep in mind that your intensity values did not change from, I think it was aluminum that we had used as our reference graph. but the angles did change, and that was what was expected of us in this question. That is pretty much homework 2. Like I said, it was not a very difficult homework except for question 9. Going back up to this, the reason I put this in here is this is SiO2, and this is its weird structure. I know Dr. Linus told us that a lot of these questions on the exam will probably be harder, and this was a good practice question for drawing directions through and planes through and seeing where atoms, how many atoms were on the plane or how many directions were on the plane. I personally had a lot more challenges with trying to figure it out for this structure, solely because it's really weird and you have 4 tetrahedral atoms in between that throw me off personally. But it is good practice, and I do believe there's questions in the textbook revolving around SiO2's structure, so I recommend practicing those. These are some common Miller indices planes. So right here, these negative ones could go in either direction depending on where you choose your origin to be. So likewise over here, these do not have alternatives because you have zeros and infinities do not just change. But that's pretty much it. I would practice this if you need more understanding on linear density, or trying to find directions, or trying to find how many atoms lie on a plane, how many atoms lie in that particular direction. Or you could just draw the 1, 1, 1 direction, 1, 1, 0, 1 half. There's multiple that you could try out, but it's worth trying out on this structure and trying to understand it a little better. Or just trying to find the number of atoms in this unit cell took me a while. So, yep, definitely try that out. And I think that is it for homework 2. If you have any questions, me and Carl are more than available to answer them. Have a good day, guys.